Yeah, because some of you haven't just like registered the course maybe after the first week. So in that case, I'll send another email maybe today or tomorrow, so you will get the appropriate information to join the Google Classroom webpage. Okay. So yeah, so don't worry about it. And if you have any question, you can just email me at any time. Okay, so I think we can start today's lecture. And okay, so I think we have mentioned in the last course that we are going to start our lecture from the study of mean field theories. Okay, so the reason we want to study the mean field theory is because in the statistical mechanics one, you probably already reviewed the course, and you will find that one of the very important information from the statistical mechanics one is to formulate statistical mechanics. And the important idea is like the ensemble theories. Okay, and then in order to understand ensemble theories more, we use some simple examples such as ideal gas models. And it is simple because it is almost like a non-interacting system. So that when you write down your partition function is factorizable. And once it is factorizable, a many-body system actually is reduced to a single particle physics. Okay, so once you know how to deal with a single particle, you know how to deal with n particles. So that's why this is a starting point where we try to introduce the idea of ensemble theories. So a little bit, complicated example is like the Ising model. And Ising model is probably one of the simplest interactive models that we are dealing with in the last semester. So basically, Ising model looks like this. You have a Hamiltonian, basically the energy of your system. That looks like you have some kind of exchange coupling. And the spin I and the spin J are interacting in some way. And here, Si or Sj is a binary variable. It's just pointing upwards or downwards, okay? So this Hamiltonian just suggests that when the two spins are parallel with each other, like both of them pointing upwards or both of them pointing downwards, the energy is lower. So the system prefers to have parallel spins in order to reduce their energy. Okay, so that's like a simplest non-trivial model when we deal with interacting system. So we also demonstrate that in order to solve the partition function for this Ising model in 1D, we can actually solve it exactly by transfer matrix. Okay, and once we learn how to work in this transfer matrix language, we will immediately realize that it is very difficult to generalize it into two-dimensional system. So we introduced the idea of mean field theory, which is an approach that can be applied for general interacting system, no matter what is the dimensionality of your system. Okay, so what does that mean? It means that it is very versatile. You can use this kind of framework to understand interacting systems. However, because it is very versatile, it also means that there's no free lunch. You are actually sacrifice something. Okay, so that's something that we did not really discuss in detail in the statistical mechanics 1. So in the statistical mechanics 2, we'll try to push our understanding about interacting system further and try to see what happened to the mean field theory first, and then we'll try to develop a more general framework to describe what is mean field theory. That's basically the Landau theory, okay? And this general framework is a framework that is specifically designed to describe different phases of matter, okay? But in general, you can have mean field theory beyond the equilibrium phases of matter, but I will not discuss that part because that means it basically there are just too many different kinds of variations. So I would like to use the study of different phases of matter as an example to show you that how mean field theory works in different contexts, and then bridge it to a general framework, which is the Landau theory. And then also I'll try to emphasize the limitation of the mean field theory, and this problem will also persist in the Landau theory. You will know what I'm talking about a little bit later. Okay, so that's like the plan of the course. We'll try to improve our understanding of interacting systems. Okay, so at this point, are there any questions? Like maybe you went in the last week, maybe you review what happened in statistical mechanics 1, but still have some problems about some basic ideas. Okay. Yeah. Okay. So if not, let's try to start our first new subject, which is the Landau theory. Okay. So I will motivate the Landau theory from what we have learned in the mean field theory of Ising model. Okay. So the Ising model, as I already written, that it is something that looks like this. Okay, so this is a model with the interaction because now the variable Si and Sj are interacting with each other in some way. And in the simple cases that we are going to consider, we'll only consider the coupling between the nearest neighbors, which means that if you have a lattice and maybe your spin I is sitting right here, and this ij symbol means that we only consider the j site that is next to this I site. For example, these 4 sites are the neighbor of the I site. Okay, so I'm using the 2D example, and I'm considering the square lattice system, but in general, this model can be defined in arbitrary lattice and in arbitrary dimension. So we'll focus on dimensionality that is above 2D first. So basically, the physics of the first term we already discussed, that the system, oh, by the way, I forgot the minus sign, okay. And here we assume that j is greater than 0. So the first term is basically the energetics that we prefer the spins to be pointing along the same direction, okay? And the second term is a term that's related to the external field. So consider you have a bunch of little spins sitting on this lattice, okay? Maybe 9 of them will be enough. And what this term is telling us is that if you apply a magnetic field to this system, what the magnetic field is doing is that they'll try to align the little spins in the same direction. So if you apply a external field h greater than 0, it means that you align all the spins such that it's pointing in the positive z direction. Okay. So now we are on the same page of understanding this Hamptonian, and as we described that in the last semester, we learned how to analyze this model by the technique, basically the mean field theory. Okay, so So what mean field theory is doing is that, oh, by the way, there's a very bad notation issue. So let's call this thing little h for external field and the capital H for the Hamiltonian. Okay. So what mean field theory is trying to say is that when we consider the interaction of the neighboring spins are doing something as if it is applying a effective magnetic field to the target spin. So what do we mean by that? It means that we can try to imagine that the magnetic field now is elevated by some kind of effective magnetic field that is applied on side I. And this effective magnetic field includes the part that is like from the original model, but also it includes the influence from its neighbor that is not equal to I, but they couple. Here I will just put back the labels. It just means like the coupling between ij spins. And this coupling is related to the configurations of the J spins, okay? So it means that if most of the time the J spins are aligned in the Z direction, that will enhance the effective magnetic field that is applied on the I side, okay? So in the mean field theory, we know that this is, when we do this replacement, actually, it is not complete because we should also have something that's left, which is basically the fluctuation. Oops, it's a bit tight. Let's see. So what is left is the fluctuation, which is this term. Oops. Okay, so here this Sj in the angle bracket means that it is the average value of the J spin, and Sj is the value of the spins on the side J. So this term is dropped when you are doing the mean field analysis, and we just replace the effective external field by this quantity. Okay, so. And then we move on and do the self-consistent analysis of the mean field theory. But the question that we should ask is, does it make sense? Okay, so let's try to think about the behavior of this Ising model, right? So we know that this model, this Ising model, will at least have two phases. One, and there will be a critical temperature Tc, okay? And here's the T equal to 0 region. So if we are deep inside the order phase, this is the order phase, then we know that the phase that we should have is some kind of configuration that most of the spins are parallel with each other. The reason is because when temperature is very low, the entropy effect is not really important. So what you need to consider is the energetic effect first, okay? So in this Hamiltonian, you can realize that when temperature is very low, and let's assume that H is 0 for the interesting spontaneous symmetry breaking case. So when the temperature is low and H is 0, then basically the energetic is dominated by the first term. And to minimize the first term, what you want is actually all the spins pointing in the same direction, okay? So we know that at very low temperature, or deep, you are actually deep inside the order phase. So in this regime, actually, it actually makes a lot of sense to drop this term. And the reason is because in this, in the order phase, the expectation value of the spin is very closely to +1 or -1. So, but we just choose one of the spontaneous symmetry breaking configuration, say +1. So it means that every spin is basically sitting there, and very little chance that you will flip to the opposite direction. Okay, and because of that, this Sj minus Sj expectation value is approximately 0. So deep inside the order phase, this mean field theory should work really well. However, if we are near this region, which is nearby the region where the system is about to change its configuration into the disorder phase. And why this region exists is because at a really high temperature, we know that basically the energetics is not really important because entropy is really important. So the system will try to go to the maximize the entropy configuration. So basically, you just have a bunch of random spins, okay? So when you are nearby the transition where you are going from the order phase into a random disorder phase, what you realize is that your spin's configuration should be quite disordered and they are pretty much random. So the expectation value of Sj should be very close to 0, okay, when you are nearby the critical temperature. And when you are nearby the critical temperature and the expectation value is approximately 0, then this quantity will be approximately equal to Sj, which is something like of order 1. So it is not obvious that actually mean field theory can be justified because this term or this effect of fluctuation is actually non-negligible, okay? So this is basically one of the challenges when you try to use the mean field theory to analyze the critical behavior. So in principle, you can still use mean field theory and try to analyze the physics, and you will split out some conclusions, but you need to be careful and ask yourself how this fluctuation is taken care of. Because at the very zeroth order level, when you apply mean field theory, actually it cannot be justified. Okay. So basically, Landau theory is closely related to the mean field theory approach. So from this simple discussion, we know that mean field theory have some problem nearby the critical temperature. So when we develop the Landau theory, it will also suffer from a similar problem. So we will revisit that issue when we get a more detailed description about what Landau theory is. Then we will discuss how to take care of this fluctuation in the framework of Landau theory. Okay, so let's try to enter another very important idea to construct the Landau theory. So that's like the concept of order parameter. Also, by the way, if you have any question, please just interrupt me. Otherwise, I'll keep going and I'll go say something that's really out of control. Okay. So the idea of order parameter is actually quite simple. That basically we want to develop a theory that can capture the phenomena of phase transition. Because, like we, starting from the Ising model, we know phase transition is it's actually a very generic behavior for many body system. You can go from one order phase into another disordered phase. So the simplest criteria, if you want to develop a theory to describe such a physics, you want to have some quantity that can capture the idea whether the system order or not. And that's basically the concept of order parameters. At least like on the conceptual level. So basically, it is a quantity that describes the order Okay. So let's try to use O to denote, in an abstract sense, what an order parameter is, because the definition of order parameter could depend on different systems. Okay. So once you define some kind of quantity as an order parameter, usually what you are looking for is like the uh, statistical average of this quantity. When when the statistical average of this quantity is not zero, which means that um, you have some kind of order that's described by this O operator. So it means the corresponding order exists. Okay. And whenever this O is zero, it means that it is in the disorder phase. Okay, so the idea is quite simple. If it is non-zero, the order exists. If it is zero, then it is in disorder phase. Okay, so let's try to take the mean field theory as a simple example. So in the Weiss mean field theory, the order parameter is actually the spin I expectation value. Okay, so from our previous discussion, we know that this quantity is just a pure number. Okay. So one of the issues that that if we take the Weiss mean field theory as an example, you might think that, oh, maybe order parameter is always a pure number. And it turns out that the answer is no. You can actually apply Landau theory in more complicated example. Then the order parameter might be a vector. For example, if you consider the Hamiltonian, that is very similar with the Ising model, but the spins is now replaced by some unit vectors that can be allowed to rotate in any d-dimensional space. And usually in the case of the physical space that we live in, the spins are usually just a unit vector that's pointing in 3 dimensions. So it means that it is like some ordinary unit vector that you are familiar with. Okay. So in this case, this model usually is applied in solid-state physics when you are trying to describe some magnetic system with some rare earth magnetic ions where the electronic orbitals are quite isolated from the environment, so you can approximate your little spins as very isotropic. Okay, so in this case, when you describe your magnetic system, the order parameter you are using will be the expectation value of this little unit vector. And when it is not zero, it means that it could be some kind of non-zero value along some direction. Then the order parameter for this model will turn out to be a vector instead of a pure number. Okay, so this is a vector. Okay, but there are also some more general system, such as like a superconductor, which is also described by a Bose-Einstein condensate, and that will also be a order parameter for that system. And also, if you work in liquid crystal, you probably will also notice that there are tons of interesting phases, like nematic phase and things like that. And in those interesting systems, the order parameter is actually not a vector. It is actually a tensor. So it could be some high-rank object. Okay. So so at this moment, what I'm trying to say is that the idea of order parameter is actually quite phenomenological. It depends on what kind of system you are trying to describe, and it could be a pure number, it can be a vector, or even a tensor. Okay. So at this point, are there any questions? Okay. So if not, let's try to move on. So at this moment, we just described something that's quite vague, and it is not really a theory, but it's more like we know that we are trying to describe a system that can order, or it can be disordered. Okay, so one of the issue that we want to, or like one of the goal that we want to achieve is that can we build a theory for this order parameter by looking at the mean field theory that we already have been discussing. Okay, so so the goal or the question that we are trying to pose is can we use the idea of order parameter and okay. So the question we are asking is, given the simple notion of this order parameter, and we know something about the mean field theory, can we try to find a phenomenological theory for our order parameter and describe the mean field theory approach? Okay. So at this moment, you might say, like, why should I do that, right? Like, I have the Weiss mean field theory and it is working fine. Why should I try to, take the next level of abstraction and try to replace the nice, pure number into something that's relatively abstract and quite general? And one of the reasons is, of course, we want to have a theory that can be applied beyond the specific model, such as the Ising model. That's one of the reasons. And the other reason is that from the last semester exercise, we have done a very interesting example that when you try to develop a mean field theory for interacting gases, basically the van der Waals equation, what you can realize is that the critical exponents for the van der Waals equation actually is identical with the critical exponents of the Weiss mean field theory. Okay, so what this conclusion is telling us is that, like these two very different theories, they are somehow related with each other under a bigger framework of theory. So what Landau is trying to do is that whether we can find a more unified framework to encapsulates all these important informations into a complete theory to describe different phases of matter. Okay, so it is not completely, unreasonable thing to do. Actually, there's some very interesting hints and motivate us to try to develop a bigger theory to include both of them. Okay. So we want to capture the general structure of the mean field theory. Okay. So let me try to remind you a little bit more about what I just said. So the van der Waals equation actually can be written like this. And here, this P is actually the pressure divided by the critical pressure. So this P is a pure number. And this curl T is actually the temperature divided by the critical temperature. And the V is actually the mu, which is the inverse density divided by the critical mu. Okay, so this V is also a pure number. So in our last semester lectures or homework, we know that using this state equation and near the critical temperature Tc, the pressure can be expanded in this fashion. And here I'll introduce something like the order parameter for van der Waals equation. And you don't need to worry about the expression right now, but you can try to prove that after the lecture. It is not too complicated. Sorry, this should be van der Waals. So this eta van der Waals is actually some kind of order parameter for the van der Waals equation. And this little t is actually reduce the temperature, which is also dimensionless. Okay. So I think at some point of your homework, you already did that expansion. But what I'm trying to emphasize is that in order to get the correct critical exponent, this is the crucial equation that you want to get. Okay. So the point is, this is the okay. So in order to reverse engineer a theory that can first give us some idea about the phase transition, but also give us some idea about the appropriate critical exponents for the mean field theory. What we are looking for is that we want to have something that looks like a free energy, and it will be a function of the pressure, temperature, and this order parameter. So this is like a quote-unquote free energy. Okay. So why we say it is some kind of free energy is because at this moment we are doing the reverse engineer. We don't know what's the physical meaning of this object. But we know that if it is a free energy, we can minimize this free energy with respect to some quantity to get the state equation. So what we are looking for is that when we minimize this free energy with respect to our order parameter, and we require it to be 0, and this equation should give us this key equation. such that, we can get the correct critical exponents to describe our van der Waals equation. Okay. So doing this reverse engineering, and the next step is that how to do that. So one can argue that maybe the simplest way to guess the possible solution is that we basically try to expand the free energy according to the dependence of the order parameter. So maybe the free energy has some part that has nothing to do with this order parameter. So let's call it the P naught. Okay. And it will have also some other parts that depends on the order parameter. And the requirement is that those parts that depends on the order parameter can give me the correct state equation nearby the critical points. Okay, so a trivial way to reverse engineer that is that we put some constants that will give us the correct unit of the free energy. Okay, that's just some microscopic constant for your system. And then this term is proportional with the integral that is related to this order parameter. Okay. So let's see why there's some jumping head stuff. Okay, let's get rid of it. Okay. So let me finish this line, then you know what I'm talking about. Okay. So I think at this point you probably noticed like why it is a reverse engineer process, because what we are looking for is an equation that satisfies this expression, right? So if we want to make some kind of derivative to minimize our free energy and get the equation that looks like that, then our free energy had better have something that's related to the integral of this particular equation with respect to our order parameter. So that's basically what this term is doing, because when you are doing the minimization by taking derivative with respect to your order parameter, this term will be gone, and the derivative of this integral will just split out what's inside the integral and require it to be zero, will basically give you the correct state equation nearby the critical point. Okay. So at this moment, we are not doing something, very physical. We are just reverse engineer and try to guess what is the possible answer or what is the possible form if we were trying to form a theory for our order parameter. Okay. So, okay. So let's take a look about the Weis-mean field theory. Okay. So this is the basically if we try to reverse engineer the possible free energy form for the van der Waals equation. So how about the Weis-mean field theory? When you dig into your previous knowledge, you can try to refresh your memory after the course, but basically the key equation that you can get the correct Weis-mean field theory critical exponent is this particular equation. And probably something else. Okay. So we can apply the similar logic that we try to analyze the van der Waals equation, and we ask what kind of free energy we need to get this correct state equation nearby the critical exponent, nearby the critical point. So let's try to call this free energy gamma. Use another notation, and should be some function of the temperature and external field and the corresponding order parameter. And as usual, we have the first part of the core free energy is independent of the order parameter. And the second part of the free energy, again, we put in some appropriate, microscopic parameters such that we can have the correct unit of gamma. And then we introduce an integral over the order parameter, and that will give us the correct state equation nearby the critical point. By the way, I noticed I have an inconsistency of the notation. This should be the external field. So let's try to replace it with the little h, not the capital H, which is confusing because it looks like Hamiltonian. Okay. So basically, we are doing basically the same thing, but let's try to stare at this expression and the previous expression that we got for a moment. Okay, to get rid of this thing, just look at these two things. Okay, so basically one can notice that actually they share very similar structure. So the first thing is that these constants are actually not very important because they are not, they did not really depend on the order parameter. And when you look at the non-trivial part, which is inside this square bracket, you'll notice that first, both of them have something that is independent of the order parameter, okay? And you have something that is linear in the order parameter. And you also have something else that is proportional with the cube of your order parameter, okay? So of course, the coefficient in the front is actually not identical, but they basically share the similar structure that the corresponding free energy all looks like something like this. Okay, so the free energy expression, we need to do the integral appropriately, but the integral is quite easy to do because it's just a usual polynomial. So once you do the integral, the constant part will give you something linear in eta, and the linear term will give you something like something quadratic in eta, and the cubic term will give you something that's quartic in eta. Okay, so at this point, you probably can realize like why these two theories have very similar critical exponents, because the important state equation that is nearby the critical point actually share very similar structure. And that's all the mechanism that is behind why mean field theory of these two very different systems. One is describing interacting gas, and the other is describing some magnetic system, turns out to have the same critical exponent. Okay, so that's basically the motivation that, oh, by the way, here this B of t, this t is something that's like related to the reduced temperature. Okay, we'll discuss the importance of this t in the next lecture. But what I'm trying to do here is to show you that these two very different mean field theory has some similar structure. And it is not too crazy to postulate that if we try to use an order parameter and try to form a general theory to encapsulate these two very different mean field theory into one bigger framework. It seems like there's a hope, right? Because they share some kind of formal similarity. So in the next lecture, we'll talk about more details, or like how to formulate the idea of the Landau theory in a more formal sense, so you can know what Landau really postulates and try to get a feeling why this phenomenological theory actually makes sense. And since it is phenomenological, so one of the very important things about the statistical mechanics is try to describe what is the microscopic mechanism to make Landau theory actually reasonable approach, and it is not too crazy to do that. Okay, so now we will stop here and we'll take take questions, or if not, we'll just have a 10 minutes break. Okay. So are there any questions so far? Yes? Oh, what does that mean? It means that, you know, we know some answer, right? Like we can do the honest calculation of the Weiss mean field theory, and we can do the honest calculation of the van der Waals equation, right? It's just standard approximation nearby the TC. So what I meant by reverse engineer is that we know the state equation, right? But we are trying to ask, is it possible we try to postulate a theoretical framework to unify these two very different mean field theories? Because one is van der Waals equation and the other is the Ising model, which is two completely different systems, right? So, but we also, from the honest calculation of mean field theory, we found something that is very strange. That is basically the critical exponent of these two systems are basically the same, okay? So one of the question is why it is reasonable, right? So at this point, we didn't answer the question why it is reasonable, but if you are trying to bring these two different theories into a unified framework, then the question is like how to guess the answer. So here I'm trying to teach you a very, you know, from the scratch way to think about why getting this unified framework is reasonable. Because if there's no connection between these two, then it is very weird why I'm trying to get a unified theory, right? But from this very, you know, ad hoc way of approaching, we start from the state equation. And from what we have learned, we know that minimizing your free energy with respect to your thermodynamic quantity will give you some kind of state equation, right? So we are trying to say what kind of free energy will give you the corresponding state equation such that you have the same critical exponents. So we are doing that in these two examples by very simply try to find the free energy by hand, but not through some physical arguments, just try to guess what is the free energy. And then what we got is two particular form of the free energy. And we stare at these expressions and we realize that they all share some structure, that it is some kind of polynomial in your order parameter. And this polynomial seems to have some kind of pattern. It contains only the linear term, quadratic term, and the quartic term. So the question is, right now we are doing some formal manipulation, but are there any physical reasoning why this form of the free energy is reasonable? Okay, so that's what we are going to talk about in the next lecture, because Landau gives you some idea. Like, you don't need to know all these details about whether it is Weiss mean field or it is van der Waals gas. Okay, you can simply start from the postulate that your system has some symmetry, and from the symmetry, you can directly argue the form of this free energy. And once you do that, then you realize that, oh, the reason I got the same critical exponents at the mean field theory level is simply because the two systems might have some might have identical symmetry. So when I do the Landau argument, I will basically get, well, that sounds a bit terrifying. Something is leaking. Should I run? But anyway, that's like the logic. Yeah. So that's why I meant. That's what I mean by reverse engineer, because we are trying to get some formal structure of the theory instead of doing some physical arguments. But in the next lecture and the next lecture, I will tell you more about why it makes sense in a physical way. Yeah. At this moment, it's just some mathematical manipulation, nothing really deep. Yeah. Okay. So let's take a break and yeah. It's a bit cold. Maybe I should. Okay. So I think we'll continue about the Landau theory. Okay. So as I mentioned in the last course, in the last lecture, that at this point we are not doing anything physical. Yeah. We are just reverse engineer the structure of the theory. Okay, but the result is quite promising because it seems like there's a common structure for the possible free energy. So the key question is, what is the physical argument that justifies this approach? So at this moment, I'll try to introduce the postulates of Landau theories. Okay, and the goal for this postulate is to allow you to construct the corresponding field theory or the corresponding Landau theory by knowing what is the possible order parameter and what are the relevant couplings in your system. Okay, so let's start from the first point. So the postulate of the Landau theory is that actually there exists a quantity that looks like free energy. So basically the hope or the belief is that we can construct the free energy or the Landau free energy. Let me just call it L. Okay. And this Landau free energy will be described by the coupling constants Ki. So the coupling constants of your theory and the corresponding order parameter. Okay. So as I just described previously, the definition of the order parameter will depend on your system, but later we will describe what are the postulated properties for these order parameters in the Landau theory. And this L usually is called the Landau free energy. And one thing I want to emphasize is that this Landau free energy, to some extent, it is not really the thermodynamic free energy, but we will say more about why it is not equivalent to the thermodynamic free energy. But at this moment, we will just treat it as if it is like the free energy that we are familiar with in the thermodynamics, okay? So just keep that in mind. It is not the thermodynamic free energy, but we will try to pretend that it is the thermodynamic free energy at this moment, okay? So the postulate is that we can construct this Landau free energy and try to minimize this Landau free energy with respect to the corresponding order parameter to get the state equation. Okay, so the next task that we are facing is that how to construct this object. Okay, how to construct the Landau free energy. Okay, so what Landau postulated is that we can actually construct this Landau free energy according to the symmetry property of the system. Okay, that is this object is constrained by the symmetry of the system. Okay, let's just call this symmetry G. Okay, so it is related to some group of the in a mathematical sense. Okay, so it is also reasonable to start considering the structure of the free energy from the symmetry point of view, because eventually what we are doing is try to describe a phase that is ordered or it is disordered. Okay, so when a phase is disordered, that means that the symmetry of the system is basically identical with the symmetry that it starts with. And whenever the spontaneous symmetry breaking happens, then your system basically breaks that symmetry. Okay, so what I'm saying is that when spontaneous symmetry breaking happen, your order parameter is not zero anymore. And once your order parameter is not zero anymore, it basically breaks the symmetry G. Okay, so let's try to think about some simple examples. For example, like in the Ising model, we know that when there's no external field, the system is basically symmetric when you perform the global Z2 operation, which means that you flip all the spins at the same time. And it will not change your energy, so that is the symmetry of your system. Okay. So what happens when we enter the ferromagnetic phase, or when we enter the order phase? So what is happening is that spontaneous symmetry breaking happen. And when spontaneous symmetry breaking happens, then your order parameter becomes non-zero, which means that eta becomes 1 or becomes non-zero. It could be plus or it could be minus. But whenever eta is not 0, it means that it does not respect the global Z2 flipping symmetry. So that's why the symmetry is broken when the order parameter is non-zero. Okay. But once we know that the order parameter is non-zero and it breaks the symmetry, then we need to understand how to construct a quantity that's basically a scalar. Because free energy, by definition, it is something that does not transform as your symmetry is applied. So the second important point is that when we construct the Landau free energy L, which is as a function of the coupling constants Ki and eta, and now because eta is non-zero, this thing could break the symmetry. So in order to make this free energy invariant under symmetry G, we need to construct some terms that is basically formed by these etas, but these terms are singlet, or they transform trivially under the symmetry operation. Okay. So at this moment, it might look a bit unclear what do I mean by that, but later we'll take an example and see how it works. Okay. So that's the second postulate. Basically, the free energy structure is constrained by symmetry. Okay. And the third postulate is the analyticity of the Landau free energy. So basically, we assume that we can expand this free energy. Nearby eta around 0. And here we make a simplification that eta is homogeneous. Okay. So when eta is homogeneous, we can define the Landau free energy density by dividing the total free energy with respect to the total volume. And when it is expandable nearby eta equal to 0, it means that I should have this kind of expression. Okay. So the next postulate is that for inhomogeneous system, we require the free energy density to be a local function. Okay, so what do I mean by that? Local means that you want to construct your free energy. And then the information you need to construct that free energy is the order parameter nearby the real space position R. Okay, so it means that once you give me the order parameter at position R, and you give me some information about the gradients at that point, in principle, the gradients could be like, the first order gradient or the second order or etc. But the point of local is that you need to truncate that differentiation to some finite order. So that's why we said n is finite. Okay. So what does that mean? It means that providing the information of your order parameter nearby a neighbor of this position R, you are able to have a well-defined Landau free energy density. Okay, so locality is quite important when you construct the Landau free energy. Okay, so at this moment you might think like it sounds like a trivial statement, like why should I care about that? So the reason is that Landau free energy, since it is a local description, actually there are some important phase transition that cannot be captured by Landau free energy. For example, if the relative phase transition is somehow related to the global structure of your order parameter, or like it is related to something related to topology, then Landau free energy will not be able to describe such a transition. Okay, so the very famous example is the Koster-Saulers transition. If you are interested in that, you can try to Google the 2016 Nobel Prize. It is awarded to Professor Koster and Saulers, and also Professor Duncan Haldane. And the Nobel Prize basically is talking about the topology, and KT transition, or the Koster-Saulers transition, is related to the topology of the classical order parameter. So basically, the phase transition is driven by something that is non-local, so it's beyond the Landau free energy description. Okay, so that's one thing. And the other recipient of the 2016 Nobel Prize is Professor Duncan Haldane. The discovery he found is basically the Haldane phase, which is a phase of matter that avoid this locality description by noticing the entanglement structure of the quantum system. So basically, they provide two different scenarios to break this locality assumption. One is that maybe your classical order parameter has some non-trivial topology, and the other is that you can have some other fundamental physics that break the locality, for example, quantum entanglement. Okay, so at this moment, it looks like it is not really important, but actually there's a big story behind that. And that's the backbone of the topological basis of matter in the past 10 years. Okay. Okay, so now let's get back to the Landau free energy. So another trivial postulate for the structure of the theory is that when the temperature is above the critical temperature, we require the order parameter to be 0, and it must be the solution of the state equation. So wait a second. So this requirement is like, it needs to be able to describe the phase transition physics that we want to describe. And when temperature is below critical temperature Tc, we want the order parameter to be non-zero to solve the minimization equation. I'm not going to copy the same thing. I'll just say it is the same. Okay. So we just introduced the basic rules to construct the phenomenological Landau theory. Okay, so there are 4 of them. One is that we postulate something like that, exists, and then the second is that this free energy is constrained by the symmetry of the system, and you need to form your free energy using the order parameters. And then you assume that this free energy is analytic in your order parameters, so that you can expand it in terms of powers of these order parameters, and then with some gradients with finite order. Okay, so at this moment it looks like this is pretty formal, so it will be really helpful if we can try to apply these ideas to the system that we are familiar with. So let's try to construct Landau free energy. For the Ising model. Okay. So let's start with the case where we don't have external field. So the Hamiltonian just looks like this. Okay, and in principle, we are thinking about the system that is beyond one dimension. Okay, so let's see what we will have. So we basically, let's assume that we have a homogeneous system. So eta r is restricted to a very special value, eta, and it is independent of the position. So the Landau free energy density, according to our description, and we try to expand it in terms of these powers. So in principle, it should look like this. Okay, so I'll stop at the quadratic order and neglect what's happening here. And the reason is that, of course, when you construct a theory that you are not familiar with, you don't know where to stop. Okay, you need to write all these powers to higher orders. Oh, and by the way, because we assume it is homogeneous, so gradient eta is basically 0, so we don't have these gradients. Okay, so so in principle, we don't know where to stop the expansion, but in this case, because you know, it is a well-studied model, so we know that expanding to the fourth order already can give us the required phenomena, so we don't do higher order expansion. That's one reason. And the more profound reason actually is when you learn renormalization group, like later in this semester, you'll notice that these higher order terms actually becomes more and more irrelevant, which means that above certain order of the power, you don't really need to include them. They are not going to give you qualitative different results. So there's a more complete answer why we stop at the fourth order, but let's try to assume that we know that phenomenologically we can expand to fourth order and stop here. Okay. So let's assume that this is the form of the free energy. Okay. Since we already used the fact that we can expand it. Okay. So another very important information is about the minimization equation. So we just minimize this free energy with respect to the order parameter, and then we will get an equation that looks like this. Okay, so that is also not too complicated. We just take a first order derivative for this postulated free energy form. So let's see what kind of information we can get about these coefficients. Okay, so the first thing we can notice is that when the temperature is greater than the critical temperature, we want eta to be 0 to minimize this minimization equation. Okay, so in order for that to happen, basically we require A1 to be 0. Okay, because if A1 is not 0, basically, eta equal to 0 is obviously not a solution for this equation, right? So from this argument, we already kill one of the parameter. That's great. Okay. And the second thing is that let's take a look about the symmetry. So for the Ising model, we have a Z2 symmetry, which corresponds to the fact that you can flip all the spins, and then your Hamiltonian is not changed. So let's take a look about why it is so, because the energetics basically involve two spins. So if you flip everybody, so you pick up 2 minus sign, and 2 minus sign end up to be nothing. So your Hamiltonian is not changed under this symmetry. Okay. So in order to have a Lagrangian, sorry, not Lagrangian. Sometimes I mix that up because when you came from the field theory, you will have that problem. But anyway, so if you look at the Landau free energy, and you require the system to have this Z2 symmetry, what does that mean? It means that the order parameter, we describe it as eta, should give me the same Landau free energy as the case when the order parameter is flipped. Okay, so this is like the requirement that we want to have. However, if we have that restriction, actually we can kill half of the terms in this polynomial, because basically this term, which is linear in eta, will be gone, because it doesn't satisfy this criteria that when you flip the sign of eta, it needs to be invariant. So this term is gone, and the cubic term, the cubic term is gone because of the D2 symmetry. Okay, so that's good. We kill a bunch of them. So so now we reduce our Landau free energy to looks like this. This is the 0th order in eta term, and you have something that's quadratic in eta. And you have something that's quartic in eta. Okay. Also, another very important property that we know is that this A4, the coefficient of the quartic term, must be greater than 0. And why it is so? Because if A4 is negative or smaller than 0, then when you are minimizing your Landau free energy, you can always choose a solution that is eta is infinite. Okay, so okay, so it is another case we want, because we want to have a situation where eta can be 0 at some temperature that's below the critical temperature, and some finite value when it is above, eta is 0 when it is above certain critical temperature, and some finite value when it is below the critical temperature. Okay, so we don't want the solution that eta goes to infinite everywhere. Okay, so that's the reason why the coefficient of the quartic term must be greater than 0. Okay. So now the next question we want to ask is like, can it reproduce the behavior that we want the solution of the order parameter to be 0 when the temperature is above the critical temperature? That is when T is greater than Tc. does it satisfy this condition? And it turns out that when the temperature is greater than Tc, if the order parameter is 0, that means that we will have this relation. Okay, because all the rest of terms that related to eta are gone. So we immediately see what is the meaning of this A0. Okay, so this A0 is some kind of free energy that is contributed from the disordered configuration of your system. Okay, so to some extent it is always there, no matter whether your system is ordered or not. So when you tune your temperature across the critical temperature, this A0 will just change smoothly. It is not going to give you some singular behavior. Okay, so so that's why even though we include A0, but we don't expect it to give us some novel behavior nearby the critical temperature. Okay. So even though it is there, we are probably not going to be too worried about the behavior of A0. Okay. However, we still have two coefficients that we need to figure out how they depend on the temperature. Basically, we figure out A0, but we still need to discuss the behavior of A2 and A4 as a function of the temperature. Okay. So, as usual, we can try to expand the coefficient in terms of the temperature. So, when we are doing the expansion, the first term is, of course, the temperature independent part. And then you will have something that depends on temperature, and etc. And remember, as we already argued, that A4 must be something that's greater than 0. So whether you expand it nearby Tc or not, it has to be greater than 0. Okay? And you can also do the similar thing for A2. Of course, you will have something that's independent of temperature, and you will have something that depends on the temperature. Oops. At least at the linear order. Okay. So the next question that we are trying to answer is that what happened when we try to minimize our free energy according to its current form when the temperature is below the critical temperature. Okay, so let's just take this expression and do the simple derivative with respect to eta. So let's just do it. Looks like okay. And when you stare at this equation, you know there will be two kinds of solution, either eta is 0 or eta equal to this thing. In principle, you can have plus and minus sign, but it is not really relevant for us because in our system, or at least in this simple system, there's a Z2 symmetry. So we only take the plus 1 as to prove our point. Okay. So, so from the form that we argue, from the form of the free energy that we argue, we know that the order parameter either is 0 or equal to this value. So our goal is that we want to have our order parameter to be non-zero when temperature is smaller than Tc, okay? And as usual, we know that A4 is greater than 0. So what that means is that we want A2 to be something that will be smaller than 0 when you reach the temperature that is below Tc, okay? So let's try to stare at the form of the A2 a little bit longer. So in order to make A2 to be smaller than 0 when you cross the Tc, what you really want is actually you want this term to be 0, because if it is 0 when you cross the Tc, then this thing will be negative. And then assuming that you can have a positive value of A21, all right? So at least you can have a chance to get this non-trivial value of your eta, okay? So, so this condition actually suggests that you want to take A20 to be 0, okay? And if you take this argument as an input, then the Lagrange, the Landau free energy density will actually have the form that looks like this. So this is just the A4, but for the notation purpose, I just divide it by some constants. And this is just the A2, A2. And for the reason that will be a bit clear later, that I specifically kept the linear dependence of A2 as a function of the reduced temperature. Okay. So that will be the Landau free energy for our Ising model when we are doing the argument. Oh, by the way, we also have some constant terms, or like smooth background, came from this A naught. But here I'll just absorb this A naught, since they are smooth, into the redefinition of this Landau free energy. So this is a very simple example where you can, really follow the step-by-step construction of Landau free energy for your Ising model. And you realize that one of the very important facts to give you this form is actually the D2 symmetry. It basically kills all the up powers of this eta. And then that actually gives you some hint actually why symmetry is so important when you try to derive your critical exponents, because it basically requires the macroscopic order parameter to satisfy certain symmetry property of your system. Okay. All right. So, are there any questions so far? Yeah.
Does this Landau free energy describe non-equilibrium?
So the question is, does the Landau free energy describe a non-equilibrium system? Okay. So in this course, I probably will not talk about non-equilibrium systems, but I can tell you something about that. The first thing is that Landau free energy basically postulates that you are describing a phase that is in equilibrium. Okay, so at least at the very conventional, or at the very beginning of the Landau theory, we assume implicitly that we are discussing about equilibrium system. Okay. However, you can ask yourself, like, how to generalize this idea of the Landau free energy. And there are several ways to generalize it, but the most straightforward way is probably you start from your Landau free energy in equilibrium, and you try to poke your system, like maybe you shine a light or something, or shake it to drive it out of equilibrium, but not too much. You just drive it out of equilibrium a little bit, and then you add the perturbation about your system. Okay, so that's one way that you can try to generalize the Landau free energies framework to the non-equilibrium system by perturbative analysis. So I think there's a very good review by Hohenberg and Harplin talking about that, basically how to formulate the non-equilibrium Landau free energy. Okay, that's one thing. And other than this perturbative treatment, if you, like I mentioned, you are trying to perturb your system a little bit away from the equilibrium configuration. But non-equilibrium physics is like a broad area. In principle, you can drive your system completely outside of the descriptability of the Landau free energy framework. Basically, you are like out of the equilibrium so much that you cannot even have a well-defined concept of order parameter. Okay, so that could happen, and in that regime, basically, you need to completely drop the framework of ensemble theory. It is like ensemble and things like that. You probably need to deal with the individual particle, and you need to study something like master equation, etc. Okay, so in that sense, then people still try to do some kind of Landau theory analysis in that region, but I will say it will be a research area that I'm not super familiar with. But if I'm working on that field, I will ask like, what is the meaning of the generalized Landau free energy? Because in equilibrium, you can say the order parameter is well defined because you are talking about only the correlation or like at least the ensemble average of a local object. When you are in non-equilibrium, it means that you need to deal with something related to time. So one of the question is, if you have the time correlation, which is non-trivial, what do you mean by local in space? Okay, or do you mean like local in time and etc. So basically, it's a can of worms that's like a frontier of research. So that's why I'm not going to talk about that too much. But the generalization of the Landau theory to non-equilibrium system is an interesting, subject. If you are interested in, you can, study that in your term paper or things like that. But I will suggest, if you want to do so, try to narrow down a little bit. Otherwise, it's a huge field that you will never end your final project. Okay. All right, good question. But the point is that I probably cannot answer too much because it's a big field. All right. So are there any other questions so far from this simple argument? Let's try to pause here and think about what we have done. All right. So if we kind of understand what we are doing, then at least for the Weizmann field theory, our goal is simple. We need to analyze this free energy and see what it's going to do. Okay. So before that, let's try to remind ourselves this is the case when h equal to 0. Okay. That is sorry. Our system has no external field, so it respects the Z2 symmetry. Okay. So if we consider we have external field, but it is very small compared to other energy scales, then if we want to modify our Landau free energy, a very intuitive way is that basically we will have the terms that we argued, but we'll have some linear correction at leading order of eta that can change our change the form of the free energy. Okay. So let's see. What's the behavior of the free energy? Oh. So here we just consider different combinations. So this is the case when t equal to Tc. Tc. Let's consider this action or this free energy specifically. Okay. So to simplify our analysis, let's consider the case when there's no external field. Okay. So we can try to ask, like, what is the form of the line of free energy when h equal to 0, which is the middle column, the middle row, sorry. So when temperature is below Tc, we know that T is smaller than 0. And then assuming A is positive, so we have a negative coefficient for the quadratic part. So we expect the no free energy to look like this. It is symmetric. Maybe I should try to make it more symmetric. Okay. And when we are at the critical temperature, basically T equal to 0, we only have the quadratic term. So it will look like this and minimize that eta equal to 0. Okay. When we are above Tc, T is greater than 0, and both the quadratic term and the quadratic term are positive, so we basically still get something like this, with minimum at eta equal to 0. So this is basically what we want, because if you draw the order parameter as a function of the temperature, when you are below the critical temperature, it is something finite, and when it is above, it will be 0. Okay. So this is what happened for the continuous phase transition. And we'll discuss other scenarios in the next lecture. Let's take a 20-minute break. Okay, so let's continue our discussion about the qualitative behavior of the free energy that we just derived. So when there's no external field, we just discussed that it should look uh, like this. And from the minimization of the Landau free energy, we actually expect to have a continuous phase transition as we wanted. But the question is, what is the corresponding critical exponents? We'll leave it a little bit later when we do more specific calculation. But at this moment, let's try to think about like what happened when we consider the case when there are external field. So for this particular Hamiltonian, you can see that when there's an external field, what it is going to do is to provide some linear shift of your potential energy or your Landau free energy. So basically, it prefers to have some positive etas, okay? So what's going to happen is that at least below the critical temperature, the Landau free energy will be tilted a little bit, such that the minimization actually is achieved by choosing the positive eta. Okay, so this kind of behavior basically will also appear when you consider the case when you are at different temperature region, and the system will just prefer to have some non-zero etas. Okay, so on the other hand, when you have an opposite sign of your external field, what it's going to do is that it is going to tilt to the opposite direction. So you will expect to have something like this, and the minimization is achieved by choosing the negative etas, and similar things will happen at the critical temperature and above the critical temperature. Okay, so these are just the qualitative behavior for the Landau free energy if we consider the external field as some kind of perturbation to our system. Okay, so now let's try to check the critical exponents. So at this point, it is not obvious why we should believe that this Landau free energy capture the essential physics of the free energy. But let's try to make more precise calculation and convince ourselves we can really reproduce the critical exponents that we got from the Weissman field theory or the van der Waals equation. Okay, so let's again use the Ising model as an example. And at the very beginning, let's assume that the external field is 0. Okay, so to minimize this Landau free energy, what you can do is you just take derivative with respect to eta, and since we first consider the no external field situation, so we neglect the last term. So you just take derivative of this Lagrangian and this Landau free energy, then effectively you can solve it, and you'll realize that the order parameter as a function of reduced temperature will look like this. Okay. So if you plot it, it will look like something like this. Okay. And this is eta, and this is the temperature, reduced temperature T. So from this expression, you can directly read that the critical exponent, which is related to how your order parameter changes as a function of the reduced temperature, and you'll see that this critical exponent is 1 over 2, which is the square root behavior, as we learned from the conventional mean field theory analysis. Okay, so we check one of them, and we can try to check other things, for example, like the specific heat behavior. So when we try to calculate the specific heat behavior, we will take the assumption that this Landau free energy is really a free energy. Okay. As I will describe a little bit later, we will see why it is not true and under what condition we can literally take it as a free energy. So let's just assume that it is what it should be. So as we know that this eta needs to have this form when we minimize the free energy as a function of the eta, so we can put that back to the evaluation of your Landau free energy. So when T is greater than Tc, we know eta equal to 0, and the Landau free energy should be 0. That's good. And when T is smaller than Tc, then eta is equal to this value, which is minus AT divided by B. Okay? So you plug that information into the expression of your Landau free energy, which is AT times eta squared, and eta squared is something like this, and plus B divided by 2, eta to the fourth, which is this quantity to the square. Okay, so after some simple calculation, you'll find it looks like this. Okay, so you can calculate the specific heat, which is by definition, if we really treat it as some kind of free energy, then this quantity will be 0 when we are above the critical temperature, and it will be some value when we are below the critical temperature. Okay, so it is not a difficult calculation. You can just do it by simple differentiation, and remember that this T is the reduced temperature. That looks like this. Okay, so just do it, and you found that there's a jump at the critical temperature. So below Tc, the specific heat is some constant value, and above Tc, it is 0. Okay, so what that suggests is the critical exponent related to the specific heat alpha is basically 0, and that is the value that you got when you do the mean field analysis. Okay, so let's consider the case when the external field is not 0, and that will give us another critical exponent. And when it is not 0 but small, then at the critical point where T equal to 0, we immediately see that the minimization of this Hamiltonian, because now we require H to be non-zero, and when you do the minimization, T equal to 0, that means this term, the first term, is gone, and the remaining term is these two terms. And take a simple derivative with respect to eta, you'll get the equation that looks like this. Okay, maybe there are some coefficient, but I'll just drop it. So what you can find is that this, this should be the external field. It is the little h. So what you found is that little h is proportional to eta to q. So that means that the corresponding critical exponent under this condition is delta equal to 3. Okay. So again, it reproduced the mean field results faithfully. And the last part for this homogeneous case is that we can try to calculate the susceptibility at constant temperature, which is the derivative of your order parameter. as a function of the external field H, and taking derivative with respect to the external field at constant temperature. Okay, so again, we use the minimization equation and do this derivation. Then what you will find is that you need to have this relation that connects your susceptibility with other parameters. Okay, and as usual, we know what is the value of the etas at below temperature or above the critical temperature. So above the critical temperature, eta is 0, and we can get chi t, which goes like 1 over AT. And that suggests the critical exponent gamma plus is equal to 1, okay? And when temperature is smaller than 0, this eta goes like this. And we can just plug that in, and the corresponding susceptibility will be minus 4 AT. Again, this corresponds to the critical exponent that is approaching from the other side of the limit to be equal to 1. Okay? So basically, we reproduce almost all the critical exponents from the mean field theory. There are some other critical exponents related to the correlation function, but at this simple analysis where we assume that the order parameter eta is a constant, you are not able to access this information. So we'll just focus on what we have achieved here. So that's, to some extent, that's good because it tells us that, yes, we can use this simple hand-waving argument to get most of the critical exponents that we derived from the mean field theory. And it seems like it can be applied to a very general system as long as they have the same symmetry, right? Because at this moment, the only input that is physically relevant is the Z2 symmetry we are using, okay? So in that sense, that's very good, and it tells us that Landau theory can actually capture the continuous phase transition, at least from the simplest level that we assume that the order parameter is a homogeneous position-independent quantity. Okay. So we can also ask, like, okay, so now it seems like the Landau theory can capture the continuous phase transition and predict the correct, or at least the corresponding critical exponent for the mean field theory. So how about the discontinuous phase transition? What will happen? So in the Ising model, we know that in order to have a discontinuous phase transition, one way to do that is you apply an external field, okay? And when you apply the external field, you are not treating the effect of this external field as a perturbation. Like in the previous case, we do have an external field, but we treat it as if it is a perturbation, and we keep the Z2 symmetry, okay? So that's basically what happened here. So when H is, or the external field is not approximately 0, then basically you need to include higher order effect of this symmetry breaking term. So what you should have is your Landau free energy will look like you still have the part that respect the D2 symmetry. And at the linear order, you have this linear contribution from the external field. But also, you could have something that proportional with the cubic term of your order parameter. And the reason is basically because you drop the Z2 symmetry, which means that you allow all possible expansion coefficients. So the up powers, again, now you should not drop it. Instead, you should keep it. So if that's the Landau free energy, the minimization equation for this particular form is like this. Okay, so again, it is a simple first order derivative. So, uh, so when the external field is zero, that's like if we assume that you break some kind of symmetry, but just nearby the small field parameter, then what you expect is that what you need to do is you need to solve this differential equation. And the simplification that we drop this h equal to 0 is basically try to get us an accessible region instead of we need to really solve a cubic equation. Okay? So under this assumption, the eta can be 0 or it can be of the following form. The detail of this expression is probably not super important, but the point is that in order to have this real solution, real valued solution, what you require is that inside this square bracket, it needs to be something that's positive, okay? So if it is negative, it means that you will get something that's imaginary, which means that you will not have a real solution for your order parameter. So, so basically, the requirement is that we will need to have the real eta. We need to satisfy this inequality. Okay, and why this inequality is important? Because it will give us some temperature scale to explore. So basically, after shuffle these parameters, you'll find that the requirement to have real solutions will be this T to be smaller than this quantity. And we can define this thing to be T star. Okay. So, so actually we have two temperature scale. One is given by this inequality, that's basically this T star. Okay, so let's try to draw it. Here's a T star. And there will be another temperature scale, which corresponds to the point where you have a phase transition. Okay, so what will happen is that if you include this cubic term in this Landau free energy, its effect is that when you are above this T star, what does that mean? It means that this inequality is not satisfied. When it is not satisfied, it means that you only contain one real solution that's equal to 0. And there are no other real solutions, okay? So you are in a disorder phase because eta has to be 0, okay? And when you are below this T star, but above the T1, what does that mean? It means that within this temperature region, you could have two solutions. One is eta equal to something, and the other is eta equal to 0, okay? But the eta equal to 0 solution will always have a lower Landau free energy. So in this region, you still have eta equal to 0, but for a different reason, okay? So, so you are still in the disorder phase. When you try to keep that cooling down your temperature, what's going to happen is that there's a swapping between the eta equal to 0 free energy and the eta equal to something free energy. And the free energy for this eta equal to something will be lower than the eta equal to 0 free energy. So all of a sudden, your order parameters switch from eta equal to 0 to something with a finite value. So that's basically what happened in the first order phase transition, because if you draw the order parameter as a function of your temperature, at these two different energy scale, what you expect is that it is 0 here all the way to T1, and all of a sudden it jumps to some value. Okay, so basically this is the first order, or the discontinuous phase transition. Okay, so so this is like a hand waving derivative of the machinery, like how Landau free energy can actually help you to capture the continuous phase transition and first order phase transition. So question? Above line? Let's see. What is the question? You mean this term? Yeah, so the question is, are you asking if we don't need to satisfy the symmetry restriction, can we have some other terms? The answer is the some other term is basically this C eta cube. Because if you have something, like for example, other than the external field, you could have some other effect. Maybe it came from the symmetry, because it doesn't need to respect the symmetry. Maybe you can have some other coefficient, I don't know, G something. And it depends on how the spins are coupled with each other, things like that. But no matter what, at the leading order, you will be in linear order in eta, right? So at this moment, this H, even though we say it is something like external field, but actually phenomenologically we include all the possible symmetric breaking terms. We just collect them according to the power of eta. So yes, field is what external field is one of the source that break the symmetry that can give you this linear term. That's one. And other terms, maybe, I don't know, in some very crazy model you might have, because if you don't respect the Z2, you can have things like that, like three spins coupled with each other. Then under that situation, a reasonable microscopic origin such that it can contribute leading order in eta is the expectation value of this thing. Like, and this thing will contribute something linear in eta. Okay, so the Landau free energy spirit is that, we are trying to do a phenomenological description. Like we have all this microscopic process that could break the D2 symmetry, but we try to glue them or collect them into one phenomenological constants. So for example, we just put everything into this H and put everything that is proportional to eta cube into this C. So at this moment, we don't know what is the value of A, B, H, and C. They are just some unknown parameters. So one can ask, like, okay, so that's a theorist way of doing things. So you've got this phenomenological theory. So as an experimentalist, how should I find these coefficients? Okay, so the goal is that if you want to connect the theory and the experiments, what you need to do is that you need to predict some of the quantities that experimentalists might be able to measure. And from the measurement results, you try to fit those phenomenological parameters and use that as the ingredients of your phenomenological theory. So, so that's like the answer to your question. Does that make sense? Okay, good. Okay, so good. So we have went through relatively quickly, like what is the continuous phase transition and what is the discontinuous phase transition. So let's see. So there are some questions that we kind of shy away from. That first, we pretend L is really a free energy. But is it true? As I mentioned, it turns out the answer is no. And we also make a quite strong assumption that we assume eta of R is just eta, which is independent of the space. So it is homogeneous. So if this assumption fails, what happened? Okay. So these are important questions to get a real understanding about what the hell is Landau free energy. Okay. So so before we try to do that, let's try to introduce an important concept, which is called coarse graining. So this is a concept that people use when you try to construct field theory or continuous theory out of discrete models, and usually it is not really described in detail, and assuming that you know that, but I think it is quite important, so I will just try to describe what does that mean, okay? So let's try to imagine that maybe you have some kind of spin configurations, okay? Like a bunch of spins, and some of them are spin up and some of them are spin down, but most of them are basically pointing in the same direction, okay? Okay, so the length scale that those spins, let's try to assume that this is our target spin. So the length scale where more or less these spins are, correlated is called the correlation length, and it will be a function of the temperature. When you are reaching the critical temperature, then this correlation length will basically diverge, and a lot of spins are correlated. Okay, so what you can do, or what coarse graining is doing, is that to some extent, this correlation length is describing like how smooth is your spin configurations. So if you have a correlation length is C, and you try to do some kind of average within some length scale, for example, maybe within this length scale, which is lambda inverse. Okay, so lambda is some kind of wave vector unit stuff, and the inverse of that wave vector will be something of the length scale. So when you are doing the cross-graining or like do some average over this length scale, you are trying to replace the configurations nearby this block of spins by its average value. Okay. So what does that mean? It means that let's try to imagine that we have some kind of average value of the spins, and we describe it by m bar. Okay. So here the horizontal axis is r. Okay. So in principle, if you just measure all the spins on the lattice level, in principle you will have some very wiggling configurations of the spin configuration at different position. Okay, so yeah, maybe I should be more careful. So this is the to some extent the average value on a shorter length scale. So it's like we are cross-graining over, let's call it cross-graining over lambda 1 inverse. Okay, so this lambda 1 inverse is a smaller block. For example, this red block, and of course you can cross-grain your system using a bigger block. For example, like this. Let's call this lambda 2 inverse. This is lambda 1. This is lambda 2 inverse. Okay. So a cross-grain over a bigger block, what does that mean? It means that the fluctuation is going to be a bit suppressed. So the configuration for cross-graining over lambda 2 inverse will actually be smoother. So maybe to some extent you are averaging over this averaging to some extent. So you might have some more smooth configuration of your n bar value. So this is like the cross grain over lambda 2 inverse. Okay. So so the idea for this cross graining is that we are trying to find a description of the magnetic system, but try to sum up some of the detailed information and try to cap the important structure, or like the more macroscopic structure for these spins. Okay, so that's what this cross-graining process is doing. And we also notice that the configuration or the field that is derived by cross-graining at different length scale lambda will actually depends on this length scale lambda. So let me try to write down things in a more precise way. Basically, the magnetization M, when you average over the length scale lambda, which is centered at some position r, is defined as this. So 1 over n lambda of r. And this n lambda of r is basically the number of spins nearby the neighborhood of the position r. And the neighborhood is of the radius of this magnitude, and to raise to the d power. Okay, and in principle, this cross-grain size needs to be big enough. What we mean by big enough is that this lambda inverse needs to be bigger than the lattice constants. Otherwise, you are not cross-graining anything. And in principle, we should assume that it is larger than 1 to create a smooth configuration of your average value of magnetization M. Okay, so that means that we are averaging over a bunch of spins within this block that when the spin is sitting within this block that is centered at position R, we just take it into account and take the average. Okay, So that is basically the cross-grain magnetic field. And here, the implicit assumption is that your lattice constant A is much, much smaller than the cross-grain size, lambda inverse. And this lambda inverse length scale is actually smaller or equal to the correlation length of your system, okay? The reason that you cannot reach this correlation length is that, as we know, that once you average over the whole system, basically you only get one number. There's no information about the pattern in real space, right? So to some extent, the cross-graining process is that we want to trim down some irrelevant microscopic detail and try to replace the analysis of the microscopic degrees of freedom using this more smooth field, M, but still keep the important physics of the pattern of your collective behavior up to the length scale of the correlation length. Okay, so basically we want to capture something that's beyond this correlation length, but we don't want to have too much microscopic details that is much, much smaller than this correlation length. Okay. So that's basically the idea of cross-graining. So why do we introduce that? Because we are trying to answer this question, like what happens if the order parameter is not a homogeneous constant in space? So naively, when we try to construct the Landau free energy, we might think, oh, what we can do is that we just have different position, and at each point of L, we just calculate the Landau free energy according to the average magnetization at this position M. Okay, so in principle you can do that, but there's a problem because imagine that you have some kind of blocks that of course they are connected, but I just try to imagine that you have them and they are interacting in some way nearby the boundary. Okay, so you have a block with Landau energy L1 and another block of Landau energy L2. Okay, so if you really naively use this kind of way to construct your Landau energy, when you are doing minimization, what you are doing is that you minimize it locally. Minimize it here, so you might get some configuration eta 1, and minimize it here, you might get some configuration eta 2. Okay, so if you are doing this, doing that in this way, what that means is that there's a chance that eta 1 and eta 2 are different dramatically because there's no obvious coupling between them. Okay. So in principle, you don't want it to happen because you are considering a smooth configuration of your cross-grain field. So you need to add something to cure that behavior. So we want to suppress the difference between these two building blocks. So the term that you can add is that you consider the term that looks like this. Okay, so by the way, this length scale should be something like lambda inverse. Okay, so what this term is telling us is that if there's a difference between these two blocks, basically it costs you energy. Okay, so by the way, this presumably we have gamma prime greater than 0. So once you add this term to suppress the difference between the two blocks, then the system will try to have a smoother behavior such that eta 1 and eta 2 is not going to deviate from each other too much. So you have a better chance that your eta profile will be something nice and smooth. Okay, so if you stare at it, and also by the way, this delta is a vector of length that's basically equivalent to this cross-grain length scale. Okay, So if you have terms like that, in the continuum limit, what does it correspond to is actually a gradient term, but actually gradient square term. So the Lagrangian, after you include that, and if we replace this summation over R using the continuous variable, it will be some integral over d-dimensional space. And the Lagrangian density of M of R is the terms that does not have any gradient term inside. And you include the term that we just discussed here, but in the continuous limit, this gamma prime might be replaced by some other quantity gamma, which is a phenomenological parameter, so we don't really care about what is the exact value of this thing. And you will have the gradient term of this M field, and take it to the square. So basically, what does that mean? It means that we don't like any gradients, okay? So to optimize this free energy, what you want is actually you want this term to be zero, which is like constant. But we still allow the system to have some local fluctuation as long as the gradient term is not going to be too costly, okay? So then we can have some kind of smooth profile in our system. So, so when we try to use this kind of way of thinking, and actually we can try to replace this thing by something called LG, and this LG will be a functional of the profile of your average magnetization, and this is basically sometimes people call the generalized Landau free energy. Okay, but what's important is that now we can notice that actually the Landau free energy is a functional of the profile of this m lambda. Landau. And usually, when people write down the free energy, they did not specify this the accurate value of this cross-grain size lambda. Okay, they just suppress this lambda, and assuming that we are doing the appropriate cross-graining, such that you can write down your Landau free energy as if it is cross-grain scale independent. So basically, when we try to write everything down, and it will look like this. This is the Landau free energy, and if it is in the homogeneous case, then we don't have the gradient term, and everything is fine and easy to understand. But now, if we have the spatial dependence of our order parameter, it will look like a functional. And what this L is some kind of integral over the dimensional space of this generalized Landau free energy, which is a functional of this cross-grain field. So what exactly is this? Is basically, if you try to write it really in terms of the microscopic degrees of freedom, here the summation of SI is like we try to express it honestly as if it is a lattice model. And as we know, when we are trying to calculate the free energy, we are actually calculating the partition function in some sense, but we are average it over these Boltzmann factors, okay? However, the cross-grain process, what is the meaning of cross-grain, is saying that we are trying to include the Boltzmann factor, but with the projection, or we only, or with a constraint that the spins inside this cross-grain region will give us some average value that is equal to the cross-grain field times the number of spins inside this cross-grain field. Okay. So, so this step is actually, exact to some extent, but you need to think about or try to think about what is the meaning of that, because in principle we are including all the Boltzmann factors. Okay. But when we are including all the Boltzmann factors, we are trying to ask whether the corresponding microscopic spin configuration can give us the specific form of the cross-grain field. If it can, then it will give us the corresponding free energy-like object, which is the Landau free energy. So at this point, you can also see why Landau free energy is not really a thermodynamic free energy, because this summation is a constrained summation because of this non-trivial delta function. Okay. But also at this point, you can realize that this is actually a very interesting way to look at your partition function, because in principle, the real partition function should be summation over all the spin configuration with this Boltzmann factor. All right, and without any constraint, you just sum over all the possible microscopic configuration. But now you are trying to say, wait a second, maybe this is not the most physical sound way of understanding our problem. Maybe I should try to understand my partition function using some cross-grained field m lambda. And for each m lambda, I sum over all the spins such that these spins will give me the corresponding m lambda value. And the weight for this summation is, of course, again, the Boltzmann weight. Okay? So you're trying to take another point of view to think about what is a partition function. Instead of, summing over the partition function brute forcefully, like you just put it into a computer and run all the possibility, instead you say that maybe there's a smarter way to think about our problem, because most of the physics, if I describe it using the continuous field M, maybe the fluctuation is actually small, and I can use the cross-grain field to capture most of the physics. And maybe there are some other things wiggling around this cross-grain field, but it is like a secondary important, so maybe I don't need to worry about that too much in most of the cases. So, so that's basically the point where I hope you can pause and think about, like, what exactly is the meaning of that, because that's basically the spirit and the gist of the Landau theory. If you understand that, basically you will just understand the Landau theory, and then it will be very helpful for you to develop a future understanding about the renormalization group and things like that. Okay. So, so usually when you look up the literature, you are not going to see this kind of discrete summation. What you are usually seeing in the paper or some other reference is the continuous version of that. Basically, when you send the lattice constant A equal to 0, and you imagine that the grid size is so small that everything is continuous and smooth, and then what you are going to see is a functional integral over this field m lambda, and m lambda is the cross-grain field. And the functional integral will be, oh, by the way, sorry, I linked the wrong equation. I should link to the partition function. Okay. So you're not, most of the time, you are not going to see this delta function written explicitly, but instead, you will see this kind of expression of the partition function as a functional integral with the Landau free energy described by this cross-grain field. Okay, and most of the time, people assume that you're doing the reasonable cross-graining, so they'll just drop the dependence of the cross-graining process. So usually, if you came from high energy background, and you stare at this thing, you look like, this thing look like almost like the Lagrangian that you are familiar with when you are dealing with some kind of field theory. So that's why, during the lecture, you always heard me saying this thing is like Lagrangian. But anyway, that's what it is. So the point is that it is a different view to understand your partition function, and Landau somehow have the smart or the keen brain to identify that this is a very smart way of dealing with the interacting system, and put the mean field approach into one big framework. Okay, so I think that will be today's lecture, and we will continue next week to think about like maybe what can go wrong when you know that Landau theory actually have this structure, and how to include fluctuations when the mean field theory is not enough to describe your system. Okay, so that's it. And if you have a question, please ask me, and see you next week. Okay, so I'll stop recording now. Let's see how to do that. Here, stop recording.